Okay, so now we will go to the microwave components in a regular quantum computer. Right here, you will see that why having some knowledge in electrical engineering actually will help you a lot, and why, as an electrical engineer, you actually can work in a quantum computing company just with some basic understanding of the qubits. Yeah. So here is the quantum computer we have been talking about. Even you are AI people, it's also good because on the top, this is a classical controller, a classical computer. Basically, it can be high performance, right? It can be HPC, right? Sometimes because you need to do some very intensive data processing. In this classical part, you have FPGA. FPGA stands for field. Maybe I just write on the side. FPGA stands for field programmable gate array. So what is this? This is like the company like Xilinx, and then yeah, what's the one just spun off by Intel?
Xilinx.
That was the Altera. Yeah, it was Altera a few years ago. Intel acquired it because they're also FPGA, but now they spin it off again. Field programmable gate array. The interesting thing is that it's an IC chip, but they make it that so you can program it to do whatever you want. And in that sense, taping out an IC chip is very expensive. You need to tape out maybe 1 million in order to be cost effective. But sometimes you just want to test different things, right? And you just have very small volume of production, maybe medical equipment or quantum computer, for example, right? So they allow you to do a lot of debugging. You can program it for different logic, program it as a CPU, GPU. And you can imagine when it is so flexible, it must be slower than a dedicated chip. Like, for example, you can use FPGA to emulate any system. And by the way, let's Synopsys, they have an emulation software system, and they use FPGA. They have this service. So they use this to, like, for example, your iPhone, right, or cell phone, from starting, booting, all the way to running, you need this type of emulation before you bring this to the market, right? So they use a lot of FPGA, right? So, but it is still very fast, FPGA, compared to other discrete logic, right? So this is field programmable gate array, and the good thing is you can program it. Python code, of course, so you probably have some CPU, GPU if you want. AWG is the arbitrary waveform generator. And you probably understand why, right? Remember what we said last time about the gate pulse, the manipulation pulse to a superconducting qubit? It was a shape that it is not common, right? So you want to generate a certain shape of pulse, for example, this one, like this. Okay, so how do you generate this? So you can program it. It is so easy, right? You just say, okay, at 10 microsecond, 10 millivolt, 11 microsecond, 12 millivolt. You just digitize it, and then you generate the waveform that you want. So this is just purely classical. Everyone work in EE, you should have learned. You probably have taken classes in FPGA, in digital control, Python, right? So basically, you know how to program this. It's going to then send out a pulse, but this pulse is still at low frequency, right? You do not expect this AWG can generate 5 gigahertz pulse, right? Because for 5 gigahertz pulse, if you just generate a sine wave with high frequency, yeah, if you have this speed, you can do it, but you cannot do it so fast. So what you will do is to go through, you generate a low frequency and go through a local oscillator. LO is the local oscillator. right? And those who have taken RF electronics, you know what it is. It is very important. It's just a high quality oscillator, right? It can be LC tank, and it will oscillate a certain frequency. Then we go through something called mixer. Mixer basically is a multiplier. You multiply it, then you bring the frequency to the right frequency, that like 5 gigahertz that we want for our qubit. So still classical. Then we go down, this is very bulky, generates a lot of energy and heat, right? So we put in room temperature. Then you go down through the attenuator, minus 20 dB, another stage to 4 Kelvin, to 700 millikelvin, to 10 Kelvin, where the qubit and resonator reside, right? This pulse will then interact with the qubit and then change it. So let me fast forward. This is the pulse we are talking about. This pulse will then interact with the qubit and then cause it to go through this Hamiltonian, and then you have the rapid oscillation, then the qubit state will change. That's one thing, right? Another thing is we discuss about the readout. Remember how we read out the state of the qubit in superconducting qubit? Who remember? Huh? Cross curve, right? So this resonator, this is a 3D cavity we just discussed. Still 3D cavity. It has a certain mode, right? Its resonant frequency, the mode that you did in HFSS, let's say 7 gigahertz, is going to change when your qubit is zero state or one state. It can become 7.1 gigahertz, 0.01 gigahertz, or 6.99 gigahertz if the cross curve is, the cross curve is 10 megahertz. Yeah.
So in this case, would every qubit has
in principle, yes. Yeah. When you are reading or what? So if you're not doing anything, the qubit just sit there, right? And we hopefully there's no photon, it just sit in the resonator. Hopefully it doesn't interact with the environment and become decoherence. And then when you read it, you shoot the pulse to here, and then you interact with the resonator. Because the resonator mode has changed already, then we get a different phase, right? We get a shift in the frequency. And if you're doing manipulation, this one, here we just directly couple to the qubit. You can also couple through the resonator and the qubit, a little bit more complicated. But let's say you couple directly to the qubit, then it will manipulate the qubit. Do I answer your question? Okay. Yeah. So, okay, it doesn't need to be Python. The reason I wrote Python is the one that I've been using is in Python. That was by a company called Quantum Machines. Okay, they just sell this. They don't care about the bottom. Okay, and they just sell this because they then make this very easy, because what you're going to do, it's okay if you want to send this pulse, you want to program it yourself. If not, you can just write the code, say I want to apply a NOT gate, then you will just convert everything to here, to this pulse. Yeah. Yeah, so it doesn't need to be Python, depends on the vendor. And then if you read out, if this manipulation you are done, right? Read out, then you will go through an amplifier. This is the quantum amplifier. We will discuss a little bit more later. The so-called quantum amplifier means that it's at the least noise to the least possible noise to the signal. So we don't go this into detail, but you just trust me. When you try to amplify something, you actually will add noise. Okay? First of all, when I'm talking, I add a speaker here, and let's say the speaker will pick up my voice and also pick up the noise. So the noise and the voice will be amplified. The one voice is the signal. The signal and the noise will amplify by the same amount. So the signal to noise ratio won't improve, right? Do you get it? When you do amplification, right? But because it is electronics, it's going to add additional noise. after amplification. So every amplification actually reduces the signal to noise ratio. Okay, so if someone try to sing in front of you, actually if he or she actually use a mic, it should be worse because after amplification, the signal to noise ratio get worse. In principle, it is worse, right? But because you are far away, you even cannot hear anything, even you have a better signal to noise ratio. That's why they need amplification, need the microphone, right? So you can hear the voice clearly, the signal clearly, but however, the noise signal to noise ratio, it is worse. So then you come to a problem. Can we have an amplifier that does not add additional noise to it? Unfortunately, no. And that is limited by the Heisenberg uncertainty principle. So here it used quantum mechanics to do the amplification. It does not have a very high gain, but it adds the least noise to the system. Okay? And then we further amplify by a regular CMOS, for example, this is gallium arsenide high electron mobility transistor, which add also not much noise to the system when you amplify, and then the regular amplifier at room temperature. Eventually, we have the mixer to bring down the frequency, and then you get a lot of data, and then you need to do a lot of data analysis here. So you may feel that looks like simple. Why I didn't need a big computer? That is because for every measurement, we need many measurements to be sure, because we measure statistics, right? It will collapse. So we need to do a lot of readout. At the same time, we actually need to analyze the waveform, right? We will repeat again later. But if you remember, we actually try to look at the phase, the shape, the real and imaginary part of the waveform in order to determine whether the resonator has shift up or shift down, and that's the qubit state. Any questions for this big picture? Yeah. Oh, it should be in the dilution refrigerator chamber. So, for example, right, usually it is Josephson circuit. It basically sometimes can be just on chip, on the same chip. Yeah. So I drew it this way. So this is another, from 3D cavity. So you don't integrate it. Yeah. I think usually sometimes they even don't add the quantum amplifier. I know that in some system, they think that is enough, right? But if they use it, what I see usually is either JPA or tuber. They won't add two. Yeah, but I can be wrong. But usually that is the case. But you can add more if that is beneficial. Yeah, and this is expensive. That's like 20,000 or something, just an amplifier. Yeah. Yes, we have the qubit here you cannot see. So maybe this is the transmon, let's say, the cross. There's a tiny transmon over there. So they can interact with each other. So this is exactly the same as your project. Except that in this project, we don't have this nice and more proof structure, which is a very simple cuboid, right? But I still have two ports, right, in and out. And then you just put the transport on the sapphire. So that is not a good qubit. I did not give you a good design. Yeah. Okay. Okay, then let's just recall what we said last time about 1 qubit gates for the transmon. What we care about here is, we rush a little bit, right? But if those who want to go into detail, please study yourself from the textbook. I won't test the details. But the main point is that we generate this signal, S of t, psi omega 1t plus phi. We want this one to go into the qubit, right? So S of t is an envelope function. And based on this, you see S of t is going to determine the rapid oscillation frequency, omega r. Right? Well, I did not repeat this last time, but if you go back to map this to your spin qubit, which we learned earlier, omega r is the rapid frequency, right? The frequency that you flip the qubit from top to bottom, right? And we also want to emphasize that we define a quantity I cosine phi and Q equal to negative psi phi. Phi is the phase, remember, this is the phase. The phase of the pulse we send out from here, the phase of the pulse, right? And this I and Q eventually, if we try to work in the rotating phase and rotating wave, this I and Q will determine how it rotates about the x and about the y axis. This one might make you feel very confusing again. Maybe you suddenly lost all the connection, but just recall, we have done the rotating vector on the broad sphere, rotating magnetic field on the xy plane before. Remember the rotating magnetic field? If you solve the Hamiltonian, you come up with something like this. And at that time, we say you have a sigma x, sigma y. Basically, sigma x, the I will determine how fast you rotate about x, and Q will determine how fast you rotate about y. So maybe you forgot already, but now just pick it up as, when you have a Hamiltonian, you have the term related to sigma c is the rotation about the z-axis. Sigma y about the x-axis, and sigma x about the x-axis, and sigma y about the y-axis. And again, due to this Euler rotation, right, you only need to be able to rotate about two axes with free rotation. You can build any 1 qubit gate. Any questions? You recall this? Something, right? We talk about, of course, you cannot recall the equation. It has been a while, but you go back to map it. But you recall what we talked about earlier, right? Okay. So, our goal is to create this signal. How do we create this signal from the system? First of all, we talk about the mixer. This is purely RF, what people usually use in RF. A mixer is that I commute a signal. Then I have a local oscillator. This is LO. Right? This is LO, this one. So they have different frequency. For example, how about I say this is 0.1 gigahertz, right? This is not the case in RF case, okay? But now I use our case. I have a signal that is 0.1 gigahertz. And this is 5 gigahertz, for example. What a mixer does is actually is going to create two frequencies. Right? So this is in the frequency domain, this is the LO, and this is my signal. Right? So in the frequency domain, you do Fourier transformation, you will get a positive and negative frequency. This is 1 gigahertz, this is negative 1 gigahertz. This is negative 5 gigahertz. This is 5 gigahertz. And that's why it doesn't make sense here, because you see, in the RF, this one usually is larger, right? So how about I change it a little bit? Let me not do this. Let me call this 10 gigahertz, okay? Maybe that will be easier for you to understand later. Because I already emphasized this is just the RF application, not what we are having here. But I want to illustrate how it works as a mixer. Let me just call this 10. But instead of 10, in order to see the 10, let's just use 10. Okay? So mixer, what does it do? It do multiplication. And in multiplication, when you go to Fourier transform or Laplace transformation, is the convolution. Okay? And In other words, you are going to get 4 different frequencies. This is 10 minus 5. This is negative 10 minus 5. This is 10 plus 5. This is negative 10 plus 5. So you get negative 15 gigahertz, negative 5 gigahertz, 5 gigahertz, 15 gigahertz. Okay? Then the final step is to apply the low pass filter, this one. The low pass filter is going to filter everything, and eventually I will get 5 gigahertz. Is this okay? The main point is that I get omega in minus omega LO. Okay, I will get this frequency. So it's okay if you don't really get it, but I hope at least you know that a mixer is a multiplier for 2 frequencies, first of all. And then you can think of it as adding and subtracting these 2 frequencies to get a new frequency. But you will get some high frequency, some low frequency, and we will use the low pass filter to get the low frequency part. Okay, this almost, I'm not talking about this one yet, right? So now let's look at what we're doing. So when I was preparing this slide, I realized that I have a lot of typo in my book. So a pretty serious typo because I filtered the low frequency one. Okay, so here I correct the typo, so please look at this. So this is how we generate this signal that I mentioned earlier, right? This is the signal we want. This one. We want this signal to go to the qubit. So basically I want the signal to be here, right? So I want to generate this signal. Now this is the FPGA. So and the AWG. What it does is generate negative 2 S of Ti sine AWGT. Now this can be a low frequency because, as I said, the AWG responds slowly, right? It cannot generate high frequency. If it could, then we don't need mixer. For example, let's say this is 10 megahertz, right? Maybe. It has 2 ports. One is the I port, one is the Q port. You just say that you need to generate 2 different frequencies. One is I and one is Q, right? And to remind you, I equal to cosine phi and Q equals to negative sine phi. Remember, this I is the amplitude of this signal. So what I'm saying is that in order to generate this phase, I actually need to adjust the amplitude of my output at this part. Okay, so it's now this is 10 millivolt, then here might give me 20 degree, for example. Right? Okay, remember? So that's great. I don't need to generate the phase. I just adjust the voltage of my signal. Then I will be able to get the phase I want. So this signal will go through this mixer multiplied by this local oscillator. This local oscillator is a frequency, omega 1, that's what we want, plus this AWG. So this might be 5.01 gigahertz, right? Maybe, right? So that eventually I get 5 gigahertz. Okay? It will multiply to here, and then on the Q part, it will multiply by a phase shift of minus pi divided by 2 and add to here. And when I add them together, I will get this one. And that's what I'm going to show you. But are you okay with this part? So let's trace again. So what is VG at this part? VG equal to this branch plus this branch, right? So this branch is negative 2s I sine omega AWGT, right? Times cosine omega 1 plus omega AWGT. This one is the signal you have here. Okay? And then this part is negative 2SQ, right? Sine omega AWGT times this one. This one is cosine omega 1 plus AWGT minus pi over 2. I have a phase shift. I just make my circuit so that the signal has a phase shift. Is this line okay? Then I go to the next part. What I'm doing is I just substitute I as cosine phi, and the rest is the same. Substitute Q as negative psi phi, so negative become plus, so be plus psi phi. And at the same time, cosine theta minus pi over 2 is just sine theta. Okay, so cosine becomes psi. You probably forgot many equations. I also forgot, just take it for granted, right? You know what I'm doing. Then we are going to use the identity. Sine alpha cosine beta is 1 over sine sum plus sine difference. So what is this? So then it means Vg equals to, I cheat sheet, negative 2s. I won't write the t now, right? So I take out this negative 2s here, negative 2s. Okay, so I still keep cosine phi, right? So I'm looking at this line, right? Then I put sine cosine, right? This is sine times cosine. So it becomes 1 over 2 sine sum. The sum is, of course, omega 1 plus 2 omega A WG. Right? I'm doing sine alpha plus beta, sine alpha plus beta. And then plus sine, the difference. This one minus this one, right? So it is negative omega 1. So if the math is too much, you cannot follow, you just trust me, I did the right thing. You go back, right? Sine, cosine. This is sine times cosine. So sine sum, get this, and sine difference, get this. I missed the t. Is this okay? This part? Then I go to the next line. Next line, I already factor out the minus 2s, so this one becomes minus again. And then I have sine phi. And then I use the second identity, which is half cosine difference. We already know what is the difference, right? Difference is negative omega 1t. And then minus cosine sum. And we already know what is cosine sum is omega 1 plus 2 omega AWGT. Is that okay? Now, here I should add a low pass filter. I did not say that. So now we are going to add a low pass filter. A low pass filter is going to remove the high frequency term, right? Because this one has a higher frequency than omega 1. It's omega 1 plus 2 omega AWG, right? This is 5 gigahertz, this is 5.02 gigahertz. It's difficult to remove when they are close, but there is another engineering problem that you can use single sideband or whatever, right? But I remove it, so what do I get? Then Vg equals to negative 2s cosine phi. And then I'm going to remove this 2 because I have 1/2 inside, right? So it cancel. Times negative. I'm going to put negative cosine phi times sine omega 1t because sine negative omega is negative sine, right? So I take this out. The next one is negative sine phi times cosine omega 1t because cosine negative is just cosine negative theta is just cosine theta. So I get this. So these are all identity, right? As a result, you get S of t times sine omega 1t plus phi. Just use the identity. Cosine A sine B plus sine B cosine A equal to sine A plus B. Okay, so don't worry about the identity now. So what is the value of this slide? The value of this slide is just I demonstrate to you I can generate this waveform by having a local oscillator at the right frequency and then generate some low frequency signal with arbitrary waveform I want. And the phi is determined by the magnitude of these two waveforms, I and Q. And the frequency determined by the AWG and the local oscillator. This is like I make up the result by working backward, right? I just demonstrate you it can be done, but in reality, they might not use the exact math, right? So you need to be careful. But the most important thing is that by just able to working at 10 megahertz or 100 megahertz with AWG, I can generate any waveform I want, then I can bring to this signal that I can use to control QB. Yeah. The input here. Here you mean where does this go? Oh, the input I'm created is from this classical computer and controller and waveform generator. I generate a waveform like this, negative 2SI, which is cosine phi, times this frequency, which I can control very well, right? And also, I have two signals generated at the same time. Make sense? Good question. So obviously here I also need to say, right, at this point I add the low pass filter. Actually, I should add a box here in order to claim that we have this signal. Yeah. You mean if this is high? The omega one? What do you mean other frequency? What, omega AWG? Let's say like 10 megahertz or 100 megahertz, yeah. Yeah, that is the frequency that we can generate arbitrary waveform, right? If we can do it for 5 gigahertz, then we don't need this one. We just directly generate this waveform, but we cannot. Yeah.
Can you summarize the importance of this mixer again?
The important thing is that it allows us to generate a precise signal with a precise shape at low frequency, and then it helps us to bring this to high frequency. So basically it's like this. We might have a signal like this, right? And then after the mixer, it kind of bringing it to, I don't know how to say it. You know, so I try to generate at low frequency, it has an envelope like this. And then eventually it also has an envelope like this, but it's carried at higher frequency. Okay, like amplitude modulation. Okay, good. Any more questions? Yeah, so just know that we have something like this, right? And the point is, if you have learned the microwave engineering, now you know that you can do this very well. Or many students who taken the microwave class know this better than me, right? And yeah, so you can go to the quantum computing industry right away, right? Because now you understand why you need to generate this signal and what type of error you can afford. Now you probably can apply your knowledge in low-pass filter design and come up with, if my low-pass filter needs some trade-off, what trade-off should I use so that I get close to here? And why I need to get close to here? Because, hey, phi is going to determine how fast I rotate about I and Q. But at the same time, this S is going to determine the rapid frequency. So maybe for a certain gate, I want to optimize for the phi accuracy. And for another gate, I want to optimize for the rapid frequency accuracy. Right? So that's why you need this classical and quantum knowledge to optimize together. And for machine learning guy, people use this to optimize the pulse actually. They actually cannot just use an analytical one. They try to use machine learning to optimize, to come up with a S of t, not this shape, some very special shape, and they increase the fidelity of the gate. Right? So it makes sense we have EEAI and physics people here. Okay, now let's learn a little bit about another microwave electronics stuff. We have been talking about two-port network, right? The scattering matrix, the resonator, something go in, something go out. And it can be many ports, the theory. It's also the scattering matrix. Here we show the three-port network. So if it is a three-port network, it has a matrix of 3 by 3. S equal to S11, S12, S13, S21, S22, S23, S31, S32, S33. And what is the meaning of this S, right? So it is when we say Sij, the element, right? The ith row and jth column is actually equal to Vi minus divided by Vj plus when Vk plus when k not equal, maybe I better write it in another way, where Vk plus equal to 0 when k not equal to j. You don't know what I'm talking about. But let's look at the ports again. This is a microwave. And the way we analyze microwave is look at an incoming and outgoing signal, right? Do not think of a regular circuit that you use to light up your bulb, that you only have positive and negative 2 ports, and you always think about current going in one direction. Voltage is just there. It is a microwave, it's a traveling wave. So we can analyze it as a wave going in and a wave reflecting. And of course, the total voltage is the superposition of these two voltage, right? So when we say plus, it is talking about the voltage. Again, this is AC, so it's traveling. So it can go in and go. It has 2 components. Plus means going into the plot. So V1 plus going into the plot, and then I actually captured the wrong picture. Why do I do this? So the slide should be this one, right? I put the slide in the wrong part, and as a result, this picture, I will go back and swap the slide, right? So sorry for that. So this is the next slide. It should be, I should start with this slide by putting the wrong place, right? But the content is still the same, right? S equal to S11, S12, S13, S21, S22, S23, S31, S32, S33, right? With Sij equals to Vi minus over Vj plus, where when Vk plus equal to 0 when k not equal to j. Right, so that's what I'm saying. Or for every port, you have something come in, you have an input, you have output. Input, output, right? All the plus are the input, and all the minus are the output. So you see clearly, each of these is talking about S21, for example, is talking about how much coming out from port 2 when I inject something in port 1. Okay, that's the scattering matrix, right? And of course, at the same time, the other ports needs to be at 0. I want to see, because my goal is to see how much come out at I when I inject something in J. Then of course I make sure other ports has no injection, right? So this means other ports has no input, right? So this is output at port I, right? And this is the input at port J. Basically, this is the meaning of the matrix. If this is not easy to understand, we can take a look how to use it. For example, What it's saying is that this is equal to V1 minus V2 minus V3 minus equals to S11, S12, S13, S21, S22, S23, S31, S32, S33 times V in plus V1 plus V2 plus and V3 plus. That's how you use the matrix. Right? So you give me the input signal. I multiply by this scattering matrix. Then I know what the output signal are. Now, does it make sense? Make more sense? Yeah? And then, of course, you just make the other zero. You can see that the definition, what I'm giving you, is correct. Okay, so this is a three-port network, nothing special. It's just purely math. And you have learned two-port network when you're doing the scattering matrix. So there are three possible properties that we want to mention here, right? Three possible properties. Right, of a three-plot network. Right, one possible. Okay, make sure it doesn't have to be. It's just possible. It can be lossless. Can you guess what is the meaning of lossless? Not exactly. Like in a circuit, when we say it's lossless, what do you? No resistance. Yeah, so you don't lose energy. Yeah, it can still be reflected, right? So lossless means that this is a unitary matrix. We have learned about unitary gates before, right? So you see microwave is very similar, has a lot of common thing as the quantum computer. And indeed, I saw an article before when you introduced quantum computing to the microwave engineer, it just used the scattering matrix. And indeed, you can use any scattering, any circuit, n-port circuit to model a quantum gate. They will be exactly the same. However, the number of ports go up with 2 to the power n. So you want to model a 5 qubit gates, you need 32 ports, right? Because each port represents one of the components. But with that, you can model perfectly any gate because they just have the same math. It's lossless, so it's unitary. If you remember what is unitary, it means the vector, right? The inner product of the vector are orthonormal, right? When I say vector, it means this. If you take this column as V1, V2, V3, then you do an inner product between this column, Vi, Vj, they are orthonormal. That is what we learned before about a unitary matrix, right? The first is lossless. The second is that they can be symmetric. Again, they don't have to, right? And what is the meaning of symmetric? Can you guess? Oh, no, not symmetric, reciprocal. We should call it reciprocal. But then it means that the matrix is symmetric. What is the meaning that the matrix is symmetric? Say again, one say transpose, one say what? Very good. So you guys, both of you are saying the same thing. One say the transmission from one port to another port is the same as one, vice versa. And then she said it is the transpose is the same, right? So basically, it's Sij equals to Sji. Yeah. Okay, so that's okay, right? Now then I want to talk about another concept is that this is, I'm going to swap the slide when I post it, so this go back. Is that this is the third possible property. is that it can be matched. So what is the meaning of match? When it is matched, for example, we say the plot 3 is matched. So those who have learned microwave, you know matching means that there's no reflection. Okay? So it means that SII equals to VI minus divided by VI plus, right? The output divided by input of the reflected wave divided by incidence wave when the whole thing equal to 0, right? But you also need to make sure that the all other inputs, J not equal to I, equal to 0, right? So basically it's saying that the reflected wave is 0, and here say that other plot has no input, right? So this is like the case here. Here we say port 3 is matched. First, when we make sure that we don't bring any input to port 1, no input to port 2, and then when we shoot something into port 3, yeah, you will go out from to other ports, but you're not going to get any reflection, right? That's the meaning that it is matched. Okay, so maybe I can highlight this a little bit more, right? So for example, I call this 1. Other ports has no input. This is a 1. Maybe call it A. A will be better, right? And then I say no reflection. This is B, right? So you don't have reflection, right? So, however, the theory is that you cannot be lossless and reciprocal and match at the same time. Right? So I looks like did not teach you anything. Like basically, we just learned 3-port network. I hope that now you understand what is incident reflected wave. You have 3 ports. It can be lossless, then it's unitary. It can be reciprocal, then it is symmetric. It can be matched, then there's no reflection at a certain port. But the point is that they cannot be lossless, reciprocal, and matched at the same time. You can only have 2. That is just results of the matrix property. Okay, so we talk about 3-port network. And why? That is because now we want to talk about something called circulator. If we do it right, we do the 3-port network right, then we will be able to have a circulator, which means when I have an incidence wave into the port 3, it is going to only go to port 1. It won't go to port 2. And then any signal in port 1 will only go to port 2. It won't go to port 3. Any signal in port 3, it will go to in port 2, it will only go to port 3. It won't go to port 1. So you see that the signal will get circulating. And why do we want this? That is because, and let me explain later, right? So let's play with this circulator. See how to make a circulator. So in this case, we have a match and lossless network. Okay, it is not reciprocal. And because of this, because it's matched, that's why this is 0. Because SII equal to 0, because it is matched. Is that okay? And it is lossless. As a result, it is unitary. Then it means what? It means S21 square plus S31 square equal to 1. Inner product, right? The inner product is this vector inner product to its vector, right? So it's its length. Of course, it's S21 square, S31 square equal to 1. And similarly, this column has a unit length also. S12 square plus S32 square equal to 1. This column has unit length, S13 square plus S23 square equal to 1. Is this clear? Any question? Unitary means the length of every column is 1, right? And that is the definition. Another thing is the inner product between any pair of it needs to be 0. Then it means what? S12 times 0 plus S21 times 0 times S31 star times S32 equal to 0. Right? Similarly, I do S12, this row, maybe it is easier, I just write down what this is. SV1 times SV2 is just V1 inner product V2. This one is just V2 inner product V3. And this is just V1 inner product V3. Right? Again, what is V1, V2, V3 is here. V1, V2, V3. For example, take this as example. 0 times S13, 0 plus S21 times S23, S21 star S23, plus S31 times S times 0. This whole thing equals to 0. Okay, so I get this matrix with this condition because this matrix is due to the match network and this is due to the lossless unitary condition, right? So what can be the value? So let's look at this. We can assume, so we are going to design the circuit so that choose S12 equal to 0, right? You can do that. You just design your circuit so that S12 equal to 0. If S12 equal to 0, what is S32? If S12 is 0, what is S32? 1, right? Because this is 0 plus something equal to 1. Of course, you can say maybe other complex number, but let's just choose 1, right? So with this, S32 equal to 1. Is that okay? Now, because S32 equal to 1, S32 equal to 1, well, here, then what will be S31? If S32 equal to 1? 0, right? Something times 1 equals 0, then that guy must be 0. So S31 equal to 0. Maybe I should write down the equation number so that this is 1, 2, 3, 4, 5, 6, right? So when S12 equals 0, by equation 2, I get S12 equal to 0. By equation 2, I get S32 equal to 1. And then by equation 4, I get S31 equal to 2. Then I repeat, what is S3, when S31 equal to 0, then S21 is equal to 1. Yeah, so we will keep repeating now. Then S21 equal to 1. That is by equation 4, equation 1, right? And then now equation S21 equal to 1, looking at this, then S23 must be 0. Very good. Right, this is by equation 6. Now, because S23 equal to 0, then S13 must be equal to 1, right? That is by equation 3. Okay, then what is the matrix? Therefore, S equals to S11 is 0, I know. S12, I chose it to be 0. S13 is 1, right? S13 is 1. S21, 1. S22 is 0, because diagonal is 0. Let me write down the diagonal. S23 is 0. S31 is 0. S32 is 1. That is the scattering matrix of this circulator. Right? Can we learn something from here? Yes, right? Look at this. As I told you, what is V1 minus V2 minus, this are outgoing wave, right? Minus is outgoing wave, times is equal to 0, 0, 1, 1, 0, 0, 0, 1, 0, V1 plus V2 plus V3, V3 plus, right? Is that okay? This is the incident wave at different points. This is the outgoing wave. This is the scattering matrix, right? You just go through the matrix, you see clearly. V1 minus equal to V3 plus. V2 minus equal to V1 plus. V3 minus equals to V2 plus. Isn't that is saying that V3 go to V1, and then V1 goes to V2, and then V2 goes to V3. And that serves as a circulator. So I have designed a system, a 3-port network, that will circulate my signal clockwise. It won't go the other direction. Okay. Why do I want to do that? But any questions here, let me know. I know I have lots of math, right? So now you can forget everything before. The final thing, what we need is that we do have something that will circulate the signal to its adjacent neighbor. Any question here? Yeah.
Why don't you say losses?
In order to make it lossless, because if it's not lossless, you are not able to make this equation. Yeah, the inner product might not be 1. So, yeah, the choice that we make. Yeah. Yes. Yeah, V1 minus is the output, right? Yeah. So V3 will go to V1. But anyway, go into V1, will go to V2. Because minus is going out, plus is coming in. Right? So input to 3 will go to 1. Input to 1 will go to 2. Yeah. Very good. Yeah. So why do we want this? Because with this circulator, then I can do this. I'm going to match port 3 so that there will be no signal going into the system. I match it, right? This is match. And then there's no signal going to it. Then in this case, what will happen? Any V1 plus will go to V2 minus, right, as a circulator. What will happen to V2 plus, any from 1 V2? You will go to V3 minus, right? But there's no V3 plus. So V1 minus will be 0. So basically, signal will only go from port 1 to 2, but not from port 2 to 1. Right? Do you see that? Anything coming in will go to port 2. Anything come from port 2 will not go to port 1. Because it will go to 3, and then 3 cannot go to 1. Because there's nothing going to 3. Here we have port 2 here. Port 1 is at the low temperature. Can you tell me why we want to do that? Can you guess? Brief. Say it. Exactly. We do want the signal to come out so that we can detect it. But any thermal noise coming from top, we don't want it to disturb our qubit. That's why you have the isolator here. Right? So I spent so much time to go through those basics. Might not be that useful, but it's useful when one day you want to design an isolator or you want to talk to the engineer who designed this. You probably should know that it cannot be ideal, right? Then it will have a lot of rejection ratio or whatever that you need to understand. But after all, the whole idea of isolator is to have a unidirectional traffic. Your signal can only go from low temperature to high temperature, but not from high temperature to low temperature. Make sense? Yeah, this is port 1, lower temperature. Right? So you only have signal going out, but you cannot have signal coming down. Okay? Here you have no choice, so you use attenuator, right? Here, if you get this done, you are in big trouble because you don't attenuate the thermal noise, you're going to screw up all the quantum computing. Yeah. I'm not an expert here, but I believe nothing is 100%. Because the way they do that, do you know how they make isolator, circulator?
Circulated.
Yeah. Yeah. I believe they still use some active device. I forgot. Yeah, then there will be some loss. Yeah, I forgot what they do. So take a look at posters. So by the way, anyone interested in microwave electronics, take this. You can get it for free by logging into our library using your SJSU account. I don't know if you can download, but you can browse it for free. Yeah, take a look. Yeah. Oh yeah, he has a lot of book. Make sure you look at the I think it should be RF microelectronics, the title. Yeah, RF, right? Don't take the basic one. This is RF. Okay, good. Oh, so I'm slow, right? So I also still want to continue to introduce more concept. Now I'm talking about something called parametric amplification. It's not quantum, but I just want to introduce this concept. This concept is happened in classical already. Now imagine I have a LC tank. You know it very well, right? We already discussed for LC tank, the energy will convert from inductive energy to capacitive and then capacitive to inductive. Let's say it is fully capacitive, right? Because it oscillates. You should remember that it has a frequency omega L equal to 1 over square root LC, right? It keeps oscillating. Now, so at a certain time, all of the energy converted to capacitive energy, so your voltage is at the peak, right? You have all the charge plus Q and minus Q's across the capacitor. Is that okay? At this point. The capacitive energy is Q squared divided by 2C. We also studied it earlier. With Q equal to epsilon divided by D. Okay? Now, let's say at this moment, you use your hand to separate the plate very fast, right? The electron cannot move very fast because they have mass, right? It takes time. So before they leave, you move it very fast. So the Q will still be the same, right? Think about the electron on the plate. You move them away. But the capacitor will change. It becomes epsilon divided by D plus delta D. So the capacitance will reduce, right? You move it away, it will reduce, right? But the number of charge is the same, right? Then your energy will increase. Q divided by 2C because C is smaller. But it's easy to understand because this two plate has attractive force. It moves in a way you are performing a work done to the system. So you are using mechanical energy to convert it to electrical energy, which makes a lot of sense. Once it's done, then you wait because you now will convert everything to inductive energy because it's oscillating. So now you have a large current, but you don't have any charge across the capacitor. So there's no force, right? Now it's at this stage, you have 0 voltage. You quickly push them back. But when you push it back, there's no force attracting that. So you have no work done if you do it slowly, right? No work done. So it returns to the original state, correct? This is only 1/4 of cycle. You then later will oscillate back to the bottom, so you have negative Q here and positive Q here. You repeat. Then you again inject energy to it, right? So at the peak, you inject the energy. At the bottom, you also inject energy, right? Do not get confused when it is negative and plus. You swap the negative and plus because you still apply so much of force. The attraction force is still the same. So if you do this pulling 2 times every cycle, look at this, 2 times every cycle, you are pumping energy to this system and you are amplifying the system energy. That's called parametric amplification because you change the parameter of the system, which is the distance of the capacitor. Right? So by using parametric amplification, by using this way, I can amplify the signal through this parametric amplification. And this is actually like the swing. Some people like to use swing to explain this. You know how to swing. Actually, I don't swing well, so I cannot catch it. But basically, you also need to assert your force 2 times in every cycle. Then you will swing higher and higher and higher. Right? So that is parametric amplification. Nothing to do with quantum mechanics. However, this quantum amplifier is a parametric amplifier. It's very difficult, the math, right? I don't fully understand. But the point is this. When this signal comes in, it will go through a circulator. This signal will be bring to here. Remember, circulator bring your signal to the third port. And here you have a tunable Josephson junction. You will put in a flux, which is 2x of the signal frequency. Just like how I amplify the capacitor, I do it 2 times in every cycle. And then it will get amplified and go back to this transmission line and go up. That's the only thing I want to discuss. Okay, I hope you can appreciate this use circulator, right? We just say that this is a circulator. Because it's a circulator, it's not going to go directly to the output. Second, this is 2x, and I hope you can appreciate why 2x of the signal, just like what we did in parametric amplification. Like when we're doing the swing, you need to be 2x. And here you can have a voltage or magnetic flux oscillating at 2x of the signal frequency. Then you will be able to amplify the signal. Another important thing is that it adds minimum noise to the signal. That's why it's a quantum limiter amplifier, right? So this is called, you will see often QLA. Another form of them is the traveling wave parametric amplifier, tuba, right? And the reason you have the noise is due to the Heisenberg uncertainty principle. So like you go through the math, then you see that because they don't commute, and that's why you add a minimal noise figure to it. I forgot, but I will say it's just because it's Josephson, right? So I believe it's again reduced to the Q and phi. Yeah, or N and phi. So it's not charged. Actually, I don't know. I cannot comment. Yeah. But the noise is because that you have a minimal fluctuation. Because you don't commute, right? You have minimal fluctuation. And that becomes a noise because you cannot predict what it is. Yeah. Okay. Finally, let me finish these two slides also. So now you know how to bring up the signal to the frequency you want. You also know how to read it, amplify it, how to have a unidirectional propagation. But now you're at high frequency. You want to analyze it. You cannot analyze the signal directly for high frequency because your electronics are not fast enough. So we will go through something similar. We call it IQ demodulation. And again, this signal comes in, right? Now I call it AT. It doesn't need to be the same shape as the previous one. You can change. And then we go through two mixer. One mix with cosine omega 1t, another mix with the phase shifter version of cosine omega 1t. And then you go through low pass filter. Then we will get it, right? So let me show you the math. So what is VQ? We'll start with the VQ, right? What is the, so I is in phase. Maybe now I should say that this in phase. I means in phase. Q means quadrature, which has the same meaning as earlier. One is sine, one is cosine related to that. So here is VQ, right? Maybe I should not say this. I'll say this is VQ. This is VI, right? So let's look at VQ. This is purely math. VQ equal to A, I am not going to put T, sine omega 1t plus phi. This is the signal coming from the direction refrigerator times 2 cosine omega 1t. Sine times cosine equal to what? I forgot, right? So let's take a look again. Sine times cosine is half sine sum plus sine difference, right? So this is sine sum. Oh. Half sine sum. Sum is what? 2 omega 1t plus phi plus sine difference. Difference this time is just sine phi, correct? And then the math is what? I don't know. But I'm going to go through the low pass filter. Okay? Once I go through the low pass filter, this guy will be gone. Then I get A sine phi, which is equal to Q. Is that okay? Now it's just math, right? But you clearly see that by using this circuit, I can extract the phase of this signal easily, which is with just a voltage. And then I do the, oh, sorry. Let me quickly just write this right. I do the I part also. It is A sine omega 1t plus phi times 2 cosine. This time I minus pi over 2, right? So again, you go through the math. This is 2A sine omega 1t plus phi. Minus pi for cosine is the same, it's just sine omega 1t. Okay? And you go through the math. Yeah, I don't want to talk about this again next time, so I just rush a little bit. But this is just basically the trigonometry identity. You get something similar. Again, if you have the low pass filter, then you get I equal to A cosine phi. Okay? And with this, I get I and Q, which are a low frequency signal. And all I need to do is just Q divided by I, which is equals to cosine, no, sine phi divided by cosine phi, which is just tangent phi. And what is this? This is just the IQ block we mentioned earlier. You may get this point. and this is phi. With noise, then you have different point, right? So depending whether you're 0 or 1, you will have broad on the top and the other at the bottom. Then you can distinguish them, right? So you don't really need to measure the phase. You actually use this one and get the voltage, then you know what the phase is. Okay, I over time already, so yeah, you can leave now, but let me know if you have any questions. Yes, you get VI and VQ, but then you go through this low pass filter, this high frequency part are gone, right? So basically you only get the DC signal, it's just a voltage, right? And then the ratio of the voltage is tangent phi. Yeah, yeah. So one of them may be negative phi, one is phi, and then you know 0 and 1. Of course, with noise, you have a broad, right? Any question from the online student?